Good afternoon, everybody. Hope you're all doing well. Welcome back to another episode of Blockchain and Beyond. As always, I'm your host Farzan. On today's episode, we're going to be talking about quantum computing. So, I'm going to aim to build up the idea of quantum computing in hopefully an easy to understand way. I'll be using quite a few analogies to help people understand what it is. Then, I'll talk about how it can impact blockchains, and then I'll also discuss how certain blockchains in particular Algorand are modifying some of these solutions to best suit their use cases. So quantum computing is one of those strange topics where you've probably heard about. You've probably read headlines, and the headlines will read something like, these computers will break all encryption, and kind of painting a bit of a grim picture about what the future holds as a result of quantum computing. But that's not necessarily true, as there are being solutions built to counter this. So to build up the idea, so normal computers use what we would call bits, and bits are a way of representing information, and bits are either on or off. In computing terms, there will be a 1 or a 0, and you can think of it sort of like a light switch where you can turn it on or you can turn it off. Quantum computers use something called qubits, which I believe stands for quantum bits, which can either be on or off, or they can be both at the same time, which means they can be on and off at the same time, which sounds a bit confusing, but the best analogy I can think of is a bit like a dimmer switch where your light can be a little bit on but also not completely on, or it can be a little bit off but not completely off. And that's the idea that we're going with. um this picture here will represent it, but the idea is that a bit has two states, whereas a qubit can be in both of these states at the same time. The technical word for this, I believe, is superposition, where they can represent two different states at one time. So when we're doing calculations with bits, the number of outcomes is determined by the number of bits. If you only have a 1 bit calculation, there's only two possible outcomes for that bit to represent a 1 or a 0. If you have 2 bits, you have four potential outcomes. So that would be the bits representing a 0 and a 0, a 0 and a 1 and a 0, or a 1 and a 1. And there's a general formula for this to identify the number of possible outcomes, and that is 2 to the power of the number of bits. So if we had 3 bits and we wanted to know how many potential outcomes there were, we could do 2 to the power of 8, 2 to the power of 3, which would give us 8. So 8 possible outcomes if we have 3 bits. So encryption or even hashes these days use 256 bits. And to put that into perspective, that is the number 10 followed by 77 zeros. And what that should hopefully show is that it's there's a lot of possible combinations with modern encryption. And 256 bits is common, but I'm sure there's places where they use 512 bits, and also 1012 bits to encrypt or hash certain information. So it's gonna be very difficult to try break this the normal way. So if we wanted to try and break this encryption, we'd have to calculate each outcome one by one until we find an answer that works for us. So you can imagine like a line of 256 light switches, and you're trying basically different combinations to figure out which one will open the door at the end or turn on the light or whatever the situation is. And that's kind of what we're doing when we're trying to break encryption. But with qubits, the best way to describe it is you can see all of the outcomes and pick the right one immediately. And the analogy I like to use here is for Marvel fans. So when Doctor Strange is looking at the timelines in, I believe it's like Endgame, you can kind of imagine that as how qubits work. They can see all the potential outcomes, and you can basically choose the outcome which is going to work best for you, or the correct outcome basically. So it pretty much streamlines the whole process of doing these calculations one by one. Instead, it just shows you all the answers and you can pick the one that you want to use. And this is why it's a risk to modern encryption. So rather than having to calculate, 10 followed by 770 number of calculations, you will get given all of these and you can easily just pass through them instead and identify which one you need to actually break the encryption or get the right answer or de-encrypt the message that you're looking at. So that's the main threat that qubits and quantum computing can pose to modern encryption. There's usually discussions that quantum computers are hard to run, and a lot of the companies which are working on these will usually have some sort of government or state funding, which is correct. But at the same time, there's post it's called post quantum encryption, which is being developed, where the idea is that quantum computers won't be able to actually decrypt what is being encrypted, and that's what we'll move into. So we'll be looking at Falcon, and Falcon is an algorithm to sign messages that others can use to verify its authenticity. And this is quite similar to the public and private key systems that we see in blockchain and cryptocurrencies today. So a bit of background on Falcon. Falcon was actually submitted as a part of a competition in 2017 by the National Institute of Security Standards, the NIST, so NIST in the US, and this was one of the submissions, and that's quite an important factor that we'll discuss a little bit later on, because it's been a number of years and it's still a technology which is being used, which has a lot of good connotations attached to it. So I've looked into Falcon to try to understand how it works. I've got a very surface level understanding of what it does, but I'm not heavy into the math side of things, so some of these things are a little bit more complex. So Falcon uses a mathematical structure called a lattice, and a lattice is, in a very simple form, it's like a grid that can be three-dimensional. So it's like a three-dimensional graph or a three-dimensional grid, which can help you store keys, and it creates a space for you to generate key pairs. And the thing about this is that it's not easy to break with qubits as of yet. So there's no qubits out right now that can actually easily compute potential solutions to the lattice. So when you're doing a lattice, you can come up with a solution, but to try break the solution, if you don't have any other information, is quite hard. And that is the current state that qubits are in. They can't actually break this lattice mathematical structure yet. The next thing that makes Falcon actually quite interesting is to do with its performance. So even with traditional computers, so mobile phones even, and desktop laptops, Falcon is extremely fast. So the generation of a 1024-bit key takes 27 milliseconds and 29 kilobytes of RAM. So to put it into perspective, a human blink lasts around 100 milliseconds. So by the time you have blinked, you could have generated approximately 4 different key pairs using this Falcon algorithm. So that means it's really fast, which is very important because we don't want to be spending time trying to compute and generate a key. We want to be able to generate keys potentially on the fly and as quickly as possible without taking up too many resources. And the next is that it uses 29 kilobytes of RAM. So most phones have at least 8 gigabytes of RAM. I know that the Google Pixel 6 Pro, I believe, has 12 gigabytes of RAM, like by default. So 8 gigabytes of RAM translates into about 8.3 million kilobytes of RAM, compared to the 29 kilobytes which are actually needed by the Falcon algorithm. So what this goes to show is that the Falcon algorithm is still effective even on legacy hardware and equipment, meaning we can have old systems and old computers that are still quantum secure or post quantum secure. And that's quite important because it enables that sort of backwards compatibility where it can be quite expensive to replace systems, especially if you're looking to upgrade the specifications. That can be quite costly and time inefficient. So Falcon presents us a way to actually do this a lot more quickly. And the 1024-bit key is quite interesting because it can carry out about 3,000 signs every second, which means that you can sign a message 3,000 times every second. You can verify approximately 13,000 messages a second as well. So this is, much faster than a lot of what we actually need today, which means Falcon is actually quite future proof in terms of its efficiency and the capacity that it can hold. So that's kind of the general gist around Falcon. Um, but then now onto Algorand and how it extends Falcon. So Algorand is one of the post quantum secure blockchains because it uses Falcon keys. So Algorand have modified Falcon's code, adding an option for deterministic or de-randomized signing. So what this means is that given a set of variables, you're able to predict the outcome of what the signing will be. Falcon by nature includes randomization for security, but Algorand sort of de-randomizes this generation part, and this is useful for snarks, which are succinct, non-interactive argument of knowledge, which is something which comes a lot in zero knowledge proofs, and useful for sharing information across different blockchains. And so it's crucial for interoperability between systems and also potentially state proofs. That's something I need to look a bit more into about how the Falcon keys and snarks will actually impact state proofs that Algorand can also provide. So Algorand have taken this technology and modified it to fit their own use case, and they've obviously made this code public so others can review and scrutinize and look at it, which I think is a very important part of developing newer technologies. But there's also one thing that we need to be wary of in general, and this is more to do with cryptography as a field rather than Falcon in specific, is that all algorithms can have weaknesses and exploits. So there have been algorithms in the past that have been exposed as having a weakness where you can figure out what the source of the information was just by looking at the output. So part of cryptography is having the output of your algorithm completely disjointed from what you put in, and that is part of what makes a good algorithm. And so currently something like the SHA-256 hashing algorithm we consider to be quite secure because no one has found a way to actually break it and given an output, figure out what the input is in a quick way. There's only hard ways to do it, and by hard ways it's literally trying different options until you get the answer that you are looking for. So all good algorithms will come under scrutiny from other cryptographers, and this will either evolve the algorithm or kill it. And quantum computing is a potential threat to SHA-256 or is a threat to SHA-256. So we can look at this as evolution of technology and cryptography. So since Falcon has been around since 2017, it's had a good 5 years to come under scrutiny and under attack from different cryptographers trying to find weaknesses in this encryption method. Because if we are to use this widespread across all systems, whether that's banking, travel, all communications over the internet use encryption. So if we're to use this algorithm in a widespread manner, we need to make sure that it's secure enough. And that's where the entire industry of the cryptography comes in to actually scrutinize and understand the weaknesses that may come from this algorithm to help make it better for the future. So, we can see quantum computing as the killer of modern encryption, and Falcon presents the post-quantum future, but there may be a case, whether that's in 10, 50 or 100 years, where we have like a post-quantum computing stage, that puts Falcon at risk. And this is just a natural development in the cryptography space and not a specific problem of Falcon. But it's something which is quite interesting to keep in mind, that all of these algorithms are safe to use until they're exposed as being vulnerable. So there's always that to keep on the back of your minds as well. And this applies to all encryption algorithms or hashing algorithms. It's not specific to any one algorithm. So anyway, that's all I want to cover for today. It's been quite interesting looking into quantum computing. It's been a long time since I've looked at a bit more advanced maths, and looking at it here, a lot of it didn't make sense, and it took a lot of back and forth between Google and Wikipedia and different articles to help understand what a lattice structure is, and I have a very basic grasp of it. But I was able to sort of explain the situation we're in regarding quantum computers and how it can disrupt the current ecosystem, but the steps that are being uh, embedded to help protect us in the future, Falcon being one of these algorithms. But yeah, as always, feel free to reach out to me on any of my social media. Please consider subscribing or following the podcast. It would really help me a lot. But yeah, as always, until next time, thank you and goodbye.